Hello teachers, we get to start a new section today, or a new chapter, chapter 6, which is rational numbers and proportional reasoning. And in chapter 6 or section 6-1, the set of rational numbers is what we're going to talk about. So when we finish this section, you should be able to differentiate representations for rational numbers. We're going to talk about equal fractions, equivalent fractions, and the simplest form of fractions. We're talking about ordering of rational numbers and the denseness property of rational numbers. And we have a definition. A fraction or a rational number has a numerator, which is the top part of the fraction, and a denominator, which is the bottom part of the fraction. We have lots of uses of rational numbers, so let's list the use over here and then talk about an example. A division problem or solution to a multiplication problem. We've already run into that with the lectures that we've had here, where we had a division problem and our answer was not within the integers because it was a fraction, and so we introduced rational numbers to explain the answer to a division or a multiplication problem. And we have an example over here. The solution to 2x equals 3 is 3/2. And without the rational number system, that wouldn't have a solution at all. If we want to talk about portion or part of a whole, this is how we typically introduce the rational numbers. Joe received 1/2 of Mary's salary each month for alimony. Ratio. The ratio of Republicans to Democrats on a Senate committee is 3-5. That's also a fraction. A ratio is just a fraction. As a matter of fact, ratio is the root word of rational numbers. So right back up here, there you go. So rational numbers comes from the word ratio. And another use for rational numbers is probabilities. For example, when you toss a fair coin, the probability of getting heads is 1 out of 2 different possibilities, which is heads or tails. So all these are great uses of rational numbers. And we have a model for rational numbers. Drawing a picture and dividing the whole up into parts is great. So if you'll notice the first picture, we have, this is like what we call the area model. This represents the fraction 1 part out of 3, or 1/3. The number line model is great also. Notice that between 0 and 1 is divided up into 3 equal parts. So once again, the denominator is 3 in this case. But notice this time we have 2 out of 3 shaded. So that represents the fraction or rational number 2/3. And then you could also look at this in terms of sets. So there are 1, 2, 3, 4, 5. in this set, and we have 3 of them shaded, and that represents the rational number 3/5. The meaning of a fraction. So to understand the meaning of any fraction, A divided by B or A over B, where A and B are elements of the whole numbers. So remember, the whole numbers are 0, 1, 2, 3, 4, 5, and B can never be 0. Because remember, rational really is a division problem, so you're dividing by that denominator. So 0 parts of something doesn't make any sense anyway. So using the parts to whole model, we must consider each of the following. The whole that's in question, that's very important. The number B of equal size parts into which the whole has been divided, and the number A of parts of the whole that are selected. And that's really what we did with the model pictures that we used just a second ago. Now, a proper fraction in terms of A over B is where A is less than B. So the numerator is smaller than the denominator. An example of that would be 5/8 and -2/3. So we can throw the negative in front of the entire rational number. That's perfectly okay, but notice A and B are whole numbers, so they're going to be positive, and you're just saying that the whole fraction is a negative value. But notice with both of these, the numerator is smaller than the denominator, therefore these are proper fractions. You can also have an improper fraction where A is larger than B is larger than 0, so when the numerator is bigger than the denominator, that's more than a whole. An example of that would be 8/5, and negative 3 over 2. Again, notice we have a positive rational number and a negative rational number, but the numerator and denominator are whole numbers. And with an improper fraction, again, the numerator is larger than the denominator, so that would express a value that is bigger than 1 for sure. Proper fractions are between 0 and 1, whereas improper fractions are larger, 1 or larger, let me say it that way. Now here we have an example with a number line model, and the idea is that we label each of these values. So let's think how we could possibly do that. And what we need to do is to figure out how many parts we are dividing. So notice they give us the value 0 right in the center of the number line, and then 2 to the right. And how many divisions do we have between 0 and 2? So if I start counting, 1, 2, 3, 4, 5, 6, 7, 8. So we've divided between 0 to 2 into 8 parts. Well, wouldn't that mean between 0 and 1 is divided into 4 parts? So 1, 2, 3, 4, this must be the value 1. If we go backwards, let's just check, because it could be divided differently. So if I count backwards, 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, or 8 parts, let's say it that way. We didn't have to count negative. So it's divided the same way. So if I count 1, 2, 3, 4, this value should be negative 1. All right, now let's talk about our fraction values. So we know this is going to be fourths, right? Because we have this divided between 0 and 1 into 4 parts. And this would be 1/4, 2/4, so that first dot we have to the right is 3/4. This one here would be 4/4, correct? But we're simplified it as 1. 5/4, 6/4, 7/4. If we go backwards into the negative numbers, this would be negative 1/4, negative 2/4, negative 3/4, again negative 4/4, which is equivalent to negative 1, negative 5/4, negative 6/4, and this would be negative 7/4. Now negative 6/4, and we will talk about this more shortly, reduces. So there is a common divisor between 6 and 4, and I know you're already very comfortable with this. This would reduce to negative 3/2. Now let's look at the typed up answers, and they've got them labeled the same way. Notice the negative 3/2 is already reduced. I want you to notice something else. We have improper fractions. Right here's an improper fraction, here's an improper fraction, and 7/4 is an improper fraction. Why? Because those values are 1 or larger. Whereas negative 1/4 and 3/4 are proper fractions. Now let's go back to our models. Equivalent fractions are numbers that represent the same point on a number line. Notice all of these represent the same shaded region. So if we take a look, we can see that each of the whole parts, when you're looking at the entire square, is the same. Okay, all 3 of these big outside squares are exactly the same. But the first square is divided into 3 equal parts, and then the green shaded is 1 out of 3 of those parts. The second square, though, is divided into 1, 2, 3, 4, 5, 6 parts, and we've shaded 2 of those parts. But it's exactly the same as what we shaded in the first, the same area. So 2/6 is equivalent to 1/3 when we reduce that. Okay? Well, how about the next one? If we count our parts, they tell us it's 12, but we'll count for sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Definitely 12 parts of equal size. So our denominator is 12, and the green area, we've shaded 4 of those parts, so 4/12. Well, again, if we reduce that, which we haven't talked about yet, but we can clearly see from the model that they are all the same shaded region. So it must be that 1/3 is equal to 2/6 is equal to 4/12. You could also talk about this with fraction strips, where the red strip at the top represents a whole, and then you could cut 2 separate strips from the whole for the 1/2. Then you could cut 6 separate strips of the whole, and that's the green, that gives us 1/6, and we see that 3 of these 1/6, which is 3/6, is equivalent to 1/2. And you can even cut 12 strips of the whole and see that 1, 2, 3, 4, 5, 6, 12 strips is equivalent to 3/6 is equivalent to 1/2. So this is a great way to introduce equivalent fractions to students. Listen, a Hershey bar is also a great way to introduce equivalent fractions to students. Think about that. Now we have something called the fundamental law of fractions. Let's read it and talk about it. So if A over B is a fraction, and n is a non-zero whole number, and we already know that b is a fraction or a rational number, so b is not allowed to be 0. So b and n are not allowed to be 0. Then the fundamental law of fraction says that if we take a and then multiply that by n, we can also must take b and multiply that by n as well. And this is the fundamental law of fractions, and these fractions are equal. It says find a value for x such that 12 over 42 is equal to x over 210. So how could we possibly handle this problem? Okay, so what do you think we should do first? Now my thought is we really need to know how many times, or what did we multiply 42 by to make it 210. So we say 12 over 42 times n over n is equal to x divided by 210. And if you go off to the side and either use your calculator or not, we need to know how many times 42 divides into 210. It turns out that is 5 times. So what do? I say 12 over 42 times 5 over 5 is going to give me, now you check it, 42 times 5 is 210, and 12 times 5 is 60. So my answer is that x is equal to 60. Now let's see how the typed up answer goes. So notice they just showed us very quickly that 5 over 5 works because 42 times 5 is 210 and 12 times 5 is 60, and then they go on to say that your x value is equal to 60, and there it is. Now let's talk about simplifying fractions. A rational number a over b is in simplest form, or what we call lowest form, if and only if, and it looks like the word and doesn't belong here, right? Let's read that again. Is in simplest form or lowest form if and only if the greatest common divisor AB is 1. That is, if A and B have no common factor greater than 1. So let's talk about this. So for example, 2/3 is equivalent to, let's use our fundamental theorem of fractions. 2/3 times, let's multiply by 4 over 4. That would give me 8/12. Now 2/3 is in lowest terms. 8/12 is not in lowest terms. Why? Well, if you look at it as the greatest common divisor, or the greatest common factor, both of these divide by 4. We know that because we multiplied them both by 4. But the only common factor between 2 and 3 is 1, and that's why we know this fraction is in lowest terms, whereas 8/12 is not in lowest terms. So we're supposed to write each of the following fractions in simplest form if they are not already. So now we have a little bit of algebra going along here, but that's okay. We can handle this. So is 28 and 42, is there a greatest common divisor larger than 1? And when you first look, you know that 2 divides both of these, but there's actually even a larger number that divides 28 and 42, and I would argue that's 7 or possibly even 14. And really 14 is our winner. So the first thing I'm going to do, and you can do this one step at a time, is I'm going to divide each of these values by 14. So that's going to give me 2. The AB squared remains. 42 divided by 14 is 3, and you have A squared, B squared. But remember, when you divide fractions and you're dealing with variables to a power, you can simplify that even more. Now what I'm going to do is show you that this is 2AB times B, and in the denominator that's 3A times A times B times B. Now why did I do that? Because I think that you can see better actually what cancels. Notice the A's cancel, and these two B's cancel with these two B's, which is going to give me a final result. And when I say cancel, you're really dividing, right? So this is 2 in the numerator and 3A in the denominator. Now let's take a look at this typed up solution, which is probably not nearly as much explanation. Okay, so see what happened here. They rewrote 28 as 2 times 14. Instead of writing the division sign out to the side, they put 2 times 14 and 42 as 3 times 14, and they reorganized the factors. Is that okay? Sure. The commutative property of multiplication says you can write these in whatever order you like, and then they just quickly canceled the 14AB squared and the 14AB squared to get the same answer we got, which is 2 over 3A. All right, now let's see if we can use that same idea for the next problem. Okay, now A plus B squared, that really means we have A plus B times A plus B. I'm going to leave that alone for now. But I do notice that the denominator, 3A plus 3B, can be factored. Greatest common factor is 3. So if I pull the 3 out front, remember this is using the distributive property over addition in reverse. So I'm going to pull out that common 3, and that leaves me with A plus B. Now, as you can imagine, in the numerator, if you really need to see it, A plus B times A plus B is equivalent to A plus B squared. And what I can do is I can cancel this A plus B with this A plus B. And my final result is A plus B divided by 3. Now if we look at the typed up version, notice they did write A plus B squared out as A plus B times A plus B. And then they factored, the 3 comes out, and they cancel those common A plus B's. Now for example C, how about you pause it and you try C on your own and see if we get the same result. Alright, so what I hope you notice is that the numerator, x squared plus x, is x. So let's pull out that greatest common factor. I have x, and when I pull the x using the distributive property from x squared, that's going to leave me with an x. But now to represent, think backwards, x times what is going to give me this x? That's going to be a plus 1. You see that? Multiply it back in just to check. X times x is x squared. X times 1 is x. In the denominator, we still have x plus 1. And you can see that these x plus 1s factor is cancel is no different than 2 divided by 2 is 1. This is x plus 1 divided by x plus 1 is 1. And that leaves us with just x as our final result. And if we look at the typed up version, notice that's exactly what they did. They used the distributive property to factor out a greatest common factor of x. They canceled the common x plus 1s. Now what I didn't point out, and really should have, this is very important, back over here, when we cancel, really we're left with a 1. You saw my screen freaking out. we left with a 1 in the denominator. There we go. Because when you cancel here and there's nothing left, it's not like it's a 0, it's a 1. So x over 1 is equal to 1. That would make that much more clear. So if we go to look at their result, they have the 1, and then there's the x that we got, but when you cancel the denominator like that, you get the 1. Now we have an example D and E. Again, I highly encourage you to pause the video, go ahead and calculate both D and E, and we'll work on those results together. Now D might have sent you in a bit of a tailspin. When I'm looking at the numerator, I'm trying to see if there's a way that we can factor this. And there is no greatest common factor between 3 and x squared. They don't have any common factors. Now I know you see the 3 in the denominator, but those do not cancel. Neither do the x squareds. If I showed this to you in a numerical problem just to compare, so let's do 2 plus 7 divided by 2 times 7. Now we know following order of operations, we need to, because this is like parentheses on the top, I need to add 2 plus 7. We know that that's equal to 9. In the denominator, 2 times 7 is equal to 14. Now we know there are no common factors, or the greatest common divisor between 9 and 14 is 1. Therefore, 9/14 does not reduce. So we can see from a numerical problem, you can't just cancel this 2 and this 2 and this 7 and this 7. Even though the tendency is there, you cannot do that. This does not simplify at all. That is what we call in lowest terms. So this is simplest form. And if you're ever confused about, can I do this when it comes to variables in algebra, try an example with just whole numbers and see if it makes sense to cancel. And if it doesn't, then you likely cannot do this with variables either. But now the next example, we can, okay? Notice that in the numerator, I have a greatest common factor of 3. And remember, we use the term greatest common factor and greatest common divisor interchangeably. I can use that reverse distribution property to pull out that common 3. It's going to come out. Now 3 times what gives me 3? Well, there must be a 1 right there to hold that spot. And then to get the 3x squared, I would need the x squared. Again, do me a favor, use the distributive property in reverse to make sure that's right. So 3 times 1 is 3. 3 times x squared is 3x squared. We're good there. In the denominator, I'm not doing anything to that because that is all multiplication already. You'll notice that this 3 cancels with that 3, and that gives me the result 1 plus x squared divided by x squared. Now again, your tendency may be to want to cancel these x squareds, but it's the same as the story we told above. You can't cancel part of addition or subtraction. You would have to factor and cancel any common factors. So anytime you feel like you should cancel part of an addition or part of a subtraction problem, you cannot do that. This is our simplest form. And we already talked about, again, 3 plus x squared over 3x squared cannot be simplified. And then there's our simplest form that we just calculated. How about equality of fractions? We're supposed to show that 12 over 42 is equivalent to 10 over 35. Notice this says method 1. There's more than one way to pull this off. So the first way, and this might be the one that you thought about, is what if we simplify both fractions to the same simplest form? And we could show that these are equal or not. Now, if they're not equal, you might have different denominators and you still, you've got to be able to compare. So finding a common denominator might be very helpful as well. But in this problem, if you simplify 12 divided by 42 to its simplest form, think about what divides both of these. I could write 12, let me write the fraction, as 2 times 6, and I could write 42 as 7 times 6, and those cancel to give me 2 sevenths. Now if we take a look at 10 over 35, I could write 10 as 2 times 5, and I'm trying to write 35 as something either times 2 or 5, and we know 5 goes into 35. So how about 7 times 5? 5's cancel and I get 2 sevenths. This shows that these two fractions are equal. And there's the result, the same result that we got. But there's another method. You can rewrite both fractions with the same least common denominator. That's a method that I mentioned just a minute ago. So the common denominator for 42 and 35, you could use 210, that is the least common denominator, and rewrite like that very first problem we did. We could say 42 divides into 210 5 times. 5 times 12 is 60. Remember, this is the first problem that we did together. 35 divides into 202 6 times. 6 times 10 is 60. And you see that you get the same fraction. So that would also prove that these fractions are equal. Now let's take a look at a third method. So method 3 says rewrite both fractions with a common denominator. And you might be thinking, didn't we just do that? But actually we used a least common denominator. So you don't have to use a least common denominator. You could just multiply 42 times 35. And that's what they did here. 42 times 35 is 1,470. Now, you're multiplying the first fraction by 35. So you need to multiply 12 by 35 and 42 by 35. The second fraction, you're multiplying by 42. You're multiplying the numerator of 10 by 42 and the denominator also by 42. And let me show you that. So again, 12 over 42, 35 over 35. Remember, this is the fundamental fraction theorem. And 420 over 1470. And then when you multiply these both by 42 in the numerator, 42 in the denominator, you get 420 over 1,470. So you don't have to use a least common denominator. That is the point there. Now let's talk about equality of fractions. This is actually going to give us a fourth method for trying to show that two fractions are equal. Two fractions, a over b and c over d, as long as d is not equal to 0. This also should say as long as b is not equal to 0. And I have to confess, y'all, I get these PowerPoints from the book produced for publisher, and I go through them, but I don't find these little errors until I get deep into making the video, and I'm like, oh, wait a minute. So two fractions, a over b and c over d, where d is not equal to 0 and b is not equal to 0, are equal if and only if AD, notice what we're doing here is multiplying AD equals B times C. So if fractions are equal, then you can cross over A times D must equal to B times C. You recall the problem that we just worked on? We had 12 over 42. Does that really equal to 10 over 35? We could use that trick here. We can multiply 12 times 35. Let's see what that is. That gives me 420. And then the question is that equal to 42 times 10? And that's more clearly 420. And you see that means that these fractions are equal. So it's a fourth way to do it. I think that the PowerPoint should have said that as well, that this is a fourth way. And I think they were leading into that, but they didn't follow through with that. So this is a fourth way to show that fractions are equal. So again, reduce both the fractions is one way. Find a least common denominator is another way. Find a common denominator is a third way, and then use this idea that if you cross numerator with denominator of the other fraction, it should equal crossing the other way. Okay, how about ordering fractions? If A, B, and C are integers, and B is greater than 0, okay, so your denominator is greater than 0, then if and only if A is greater than C. So I've left out the important part. Then A over B is greater than C over B if and only if A is greater than C. So what's the point here? Look, if they have a common denominator to compare, all you have to do is look at the numerator. If the numerator on the left is bigger than the numerator on the right, then the left fraction is bigger than the right fraction. But listen, they have to have a common denominator to truly be able to compare them. Notice here, if A, B, C, and D are integers, and B is greater than 0, and D is also greater than 0, okay, then A over B is greater than C over D only if, now look what they did. They used that trick that we just learned. They crossed A times D must be greater than B times C. So I'm trying to cross the other way with a different color. Here you go, B times C. So numerator over times denominator of the other one. That one's greater than the other one. So you're going to have to really pay attention closely to which one gets the greater than sign. Okay, so to start with the one that's greater than numerator and cross over, and that's got to be greater than the other way multiplied together. Let's just make up an example real quick and see, right? So if we have, you know, excuse me, 11, I'm trying to lose my voice, 13ths. We don't know what goes here, greater than or less than. Let's do 15 19ths. Okay, we don't know which it goes. So let's cross this way. 11 times 19. We don't know what goes here. And then 13 times 15. And if we just type that quickly or calculate it, I'm just going to cheat and use my calculator. 11 times 19 is 209. And then 13 times 15 is 195. So we know that the arrow goes that way. Remember, mouth open to the larger number. Now that was crossing this way. That was this numerator and this denominator, which means that the greater than sign goes like that. I was disappointed they didn't have an example like that. Now I've reached my 30-minute mark. Part 2 of this video won't be terribly long because I don't have a lot left, but I don't want to cram it here. So come back and watch part 2. Shouldn't take very long, maybe 15 minutes max. If you have questions about any of this, please let me know, and I hope you have a wonderful day.